Okay, good morning, students. The last classes we have discussed about the NMR spectroscopy of protons, and we have seen that the fact that shielding effects could lead to different resonance frequencies for protons in different electronic environments. And but how do we decide uh, whether a proton is in a or a set of protons are in a different chemical environments or in the same chemical environments? For example, if you take two protons, if you label the first proton as proton 1 and the second proton as proton 2, then we call them as proton H1 and proton H2, okay, in a molecule. Then how do we decide whether protons H1 and H2 are in the same electronic environment or whether they are in different electronic environments? Okay, so we mainly decide the electronic environment, the nature of the electronic environment around a set of protons by looking at the molecular symmetry of the molecule. Okay, say for example, if you consider benzene molecule, the first one shown here, and if you consider this proton and this proton, then you can see that you can somehow interchange these protons by type of symmetry operation. For example, a C3 rotation would shift this proton to this position and this proton to this position. Okay, similarly, if you combine these two set of protons, these two adjacent set of protons, you can say that a C6 operation, rotation operation, would shift this proton to this position, right? But this will be shifted towards this position. And or in other words, if you bisect the molecule in a half, say for example in a plane which passes through the middle of these bonds, then you can easily interchange these two protons or these two protons or these two protons. So that means the protons in benzene molecule are interchangeable by some sort of symmetry operations. Okay, so then we can say that all the protons in benzene molecule are interchangeable by symmetry operation, and all the protons are in similar electronic environment around benzene molecule. Okay, the same thing here for cyclopentane molecule. If you consider each of the methylene protons here, CH2 protons here, you can see that if you bisect the molecule in a plane which passes through this plane, then you can interchange these protons and interchange these protons, whereas this proton remains there. So you can say that by doing this operation, you can basically interchange the protons here. But if you use a plane something like here, a plane passes through here, then you can interchange these two sets of protons and these two sets of protons, whereas this proton remains there. Okay, so or if you reflect these two molecules in a plane which lies in the molecular plane, then you can say that you can essentially interchange all the protons with itself. Okay, so these protons are interchangeable upon some sort of symmetry operation. And similarly, if you consider this ketone here, if you reflect the molecule in a plane which passes through the carbonyl functional group here, you can interchange these methyl protons back and forth. Okay, so these protons are interchangeable by the symmetry operational reflection. Okay, similarly, if you take tetramethylsilane, you can see that they have got something like a tetrahedral geometry, and then you can see that if you reflect in a sigma d plane, you can interchange each of these methyl protons. Okay, so all the protons in these four sets of molecule are interchangeable by applying some sort of symmetry operation on the molecule. And you can say that these protons are in the protons in benzene are in similar electronic environment, or the protons in cyclopentane are in similar electronic environment, and the protons in this molecule is in similar chemical environment, and the protons in this molecule is also in a similar chemical environment. Okay, so these kind of protons which can be interchanged by a symmetry operation, and which can be referred to as in similar chemical environments, are called chemical shift equivalent protons, or there can be, these protons can be said as in chemically equivalent environments, and they're in same chemically identical environments, and therefore they should have the same chemical shift values. That means these protons should give NMR peak in at the exactly the same frequency. For example, all the 6 protons in the benzene group will give a peak in the NMR spectrum at exactly the same frequency. Okay, whereas all the protons in cyclopentane will give, all the 10 protons in cyclopentane will give a peak in its NMR spectrum at the exactly same frequency. Okay, the frequency of all these protons in benzene would be obviously different from the frequency of all these protons in cyclopentane, but the thing is, all the phenyl benzene protons will give peaks at exactly the same frequency, whereas all the cyclopentane protons will give a peak in the NMR spectrum at exactly the same frequency. Okay, similarly, these 3 protons and these 3 protons, all these 6 protons will resonate at the same frequency in the NMR spectrum. Similarly, as I have seen that for TMS we get a single peak for all the 12 protons at delta value 0. Okay, so that is because these 12 protons are in chemically similar environments. Okay, such set of protons which are in chemically similar environments and give the same peak at exactly the same frequency are called chemical shift equivalent protons. So on the contrary, chemical shift non-equivalent protons are those protons which are not in identical chemical environments and which cannot be interchanged through any kind of symmetry process or a rapid process. In addition to symmetry process, the protons may be interchanged in chemical shift equivalent nuclei, may be interchanged by some rapid process such as rotation about a carbon-carbon single bond or a ketone tautomerism. Okay, so chemically non-equivalent nuclei, they cannot be interchanged by any kind of symmetry operation or by a rapid process that happens on the molecule, such as carbon-carbon single bond rotation or ketone tautomerism. Okay, so normally if you consider 2 sets of proton nuclei, if they are in chemically non-equivalent environments, then they give NMR peaks at 2 different frequencies in the NMR spectrum. Okay, say for example, if you consider let's start with the this molecule here. Okay, CH3CO or CH3. Okay, so this proton is connected to carbon, which is connected to carbonyl carbon, but whereas this proton is connected to a carbon which is being connected to oxygen. Okay, so obviously these 2 methyl protons are in different electronic environments. Okay, so these methyl protons will give these 3 methyl protons will give a single peak in the NMR spectrum at a particular frequency. Let's say we call that one as frequency nu1. But whereas these methyl protons, which are in a different chemical environment compared to these protons, will give again a single peak in the NMR spectrum, but at a different frequency, say nu2. Okay, now if you consider this, the last molecule here, CH3O CH2Cl, the methyl protons are connected to carbon which is being connected to an oxygen, but here the methylene protons, CH2 protons, are connected to carbon which is connected to both a chlorine and oxygen. So obviously these 3 protons and these 2 protons are in different electronic environments. Therefore these 3 protons will give a single peak in the NMR spectrum at a particular frequency, whereas these 2 protons will give a single peak in the NMR spectrum but at a different frequency. Or frequency in the sense we measure frequency as delta values in the NMR spectrum or chemical shift values in the NMR spectrum. Okay, and now if you consider this molecule here, then you can see that if you bisect the molecule through this bond using a reflection plane, then you can see these CH2 functional groups, these methylene groups, are chemically equivalent. Okay, these 2 protons can be exchanged, and these 2 CH3 protons can be also be exchanged. So this also forms a chemical equivalent set of nuclei. Okay, but if you consider the CH2 and or CH3, then you can see that CH2 and CH3 are in different electronic environments, so they form a different set of chemically non-equivalent nuclei. Okay, so you can see that similarly these CS2 and CS3 are in different electronic environments, so these two form a set of chemically non-equivalent nuclei. Okay, so you can now infer that corresponding to these two CS2 protons, okay, you will get a single peak in the NMR spectrum at a particular frequency, say nu1, and corresponding to these two sets of methyl protons, that is total 6 protons, you will be getting another peak in the NMR spectrum at a different frequency, say nu2. Okay, so these two different sets of chemically non-equivalent protons gives two peaks in the NMR spectrum at different frequencies or different delta values. Now if you consider this molecule, then you can see that a plane that bypasses or plane that bisects the molecule right through these bonds will interchange these two methyl protons and these two protons and these two protons. Okay, but the thing is, if you consider so these CS3 protons and these CS3 protons are chemically equivalent, whereas these two protons are chemically equivalent and these two protons are also chemically equivalent. Okay, but the thing is, the pair of CS3 protons forms a different chemically equivalent set of nuclei compared to the pair of these two protons, okay, and these two protons. So corresponding to these two sets of methyl protons, you will get a peak in the NMR spectrum, and corresponding to these 4 protons, you will get another peak in the NMR spectrum at a different delta value or different frequency. Okay, but what happens to the spectrum of protons when the protons can be rapidly interchanged through some rapid process such as keto-enol tautomerism? Okay, so we have seen this example before. This one is a typical molecule which can form both a keto isomer as well as an enol isomer or tautomer, and this one is a keto form and this one is an enol form. Okay, so proportionally almost 85% is constituted by enol form, and the 15% is constituted by ketone in a sample. Okay, so the equilibrium is more shifted towards the enol form. Okay, and as such you will see if you bisect this molecule right through here using a plane of reflection, then you can see that these two methyl protons are chemically equivalent, so they give a single peak in the NMR spectrum at a frequency which is right here around delta value 2.2. okay, and again this CS2 proton that is chemically non-equivalent compared to these two CS3 protons, because CS2 proton is in a different electronic environment compared to these two CS3 protons. So corresponding to this CS2 proton, you will get another peak in the NMR spectrum but at a different delta value compared to the CS3 peak. Okay, and right now once this forms the enol, then still you can see that if you bisect the molecule right through here using a reflection plane, these two methyl protons are chemically equivalent and they give an NMR spectrum, a peak in the NMR spectrum at a frequency or delta value 2. Okay, and you get the CH proton, the enolic CH proton peak at a larger delta value because it's conjugated with a double bond here. So the CH proton peak is being observed at a delta value close to 5.5 delta. Okay, but here you have got an OH group which can form hydrogen bond with another oxygen here. So this OH is not exactly 100% belongs to this oxygen, but it could belong to this oxygen to some extent as well due to hydrogen bonding. Okay, so this OH could essentially could shift between this oxygen and this oxygen. Okay, so this rapid proton exchange makes the NMR spectrophotometer to distinguish whether the proton belongs to this oxygen or this oxygen. So this rapid proton exchange, as we have seen earlier, could create a single peak for the proton at a single delta value, which is usually being observed at a around 15.5 delta value or ppm, which is quite usual because it's an enolic proton, enolic OH functional group. Okay. Okay, another rapid process that could lead to a chemical shift equivalence is rotation, a facile rotation about a single bond. Okay, but that this rotation can be restricted when the single bond turns out to be a double bond in a conjugated structure or a delocalized structure. Okay, so for example, in this molecule, you can see that these two CS3 functional group, methyl functional group, can rapidly interconvert or interchange or interexchange between among themselves by free rotation about this carbon nitrogen single bond. Okay, so around this carbon nitrogen single bond, these two methyl groups can freely interchange between each other, and essentially that makes this two sets of methyl protons chemically equivalent, and these two protons should give a peak in the NMR spectrum exactly at identical frequency. Okay, but what happens is this molecule has got a resonance structure, okay, which happens when one of the lone pairs on nitrogen gets involved in the extending the conjugation with the carbon oxygen double bond here, making this structure. Right now the bond has got a, instead of a single bond character, the carbon nitrogen bond has got a double bond character, so which makes free rotation almost impossible. Okay, we have got only a restricted rotation about double bond. Okay, so that means since free rotation is not possible about this carbon nitrogen bond, the two methyl groups are no longer exchanged by free rotation, and they are not anymore chemical equivalent. Okay, they are no longer chemical equivalent, so they give peaks in the NMR spectrum at a different frequencies or different ppm values. Okay, the first one gives a peak at a 2.85 delta, whereas the second one gives a peak at a 2.94 delta. Another process that could give chemical equivalent or erase or gives the chemical shift equivalent or chemical shift non-equivalent property to a set of protons in a ring system could be rotation about a single bond. Okay, as you can see, for cyclohexane, if you consider the chair form, the most stable form, and if you consider the axial proton and equatorial proton, and if you label them as proton A and B, right now a flipping, okay, about this one, about the carbon-carbon single bond in the ring system would give or would make the axial proton equatorial and the equatorial proton axial. Okay, so and this can be interconverted or exchanged by this flipping mechanism. Okay, so when NMR spectrophotometer try to get this peak corresponding to axial proton HA, it gets since it gets rapidly converted into equatorial proton, the spectrophotometry is no longer be able to resolve whether the proton A is whether axial or equatorial. Okay, similarly it cannot see whether the proton B is actually equatorial or axial. Okay, so this makes the protons chemically equivalent. Okay, rapid interconversion between two positions makes these protons A and B chemically equivalent. Both protons will give a peak in the NMR spectrum at exactly the same frequency. Okay, so this rotation about single bonds, as we have seen, normally gives rise to chemically equivalent protons. Okay, but it depends upon the type of substitution pattern about the carbons. Okay, so if you consider a simple substituted ethane molecule, okay, such as the one given in the first example here, you can see that 3 hydrogens are being connected to or bound to the first carbon, whereas we designate the atoms that are being connected to the second carbon as X, Y, and Z. Okay, so you can see that rotation about the carbon-carbon single bond gives rise to 2 different configurations here, but as far as free rotation about carbon-carbon single bonds uh, are spontaneous and happens spontaneously, you can see that for each substituent atoms on the second carbon, X, whether it's X, Y, or Z, with respect to each substituents, all these three protons, protons A, B, and C, are chemically equivalent, okay, because they can be rapidly interchanged. Proton, in this second example, proton A is being replaced by proton C, and the proton B is replaced by proton A, and which is being replaced as proton by proton C in the third example. Okay, so as long as all these three are the same type of nuclei, protons, then for each atoms on the second carbon, X, Y, or C, all the protons are chemically equivalent. So these three protons can be said as in the same electronic environment, and they give the same spectral peak at exactly the same frequency in the NMR spectrum. But once we substitute or replace one of the carbons on the front carbon, one of the hydrogens of the front carbon with the chlorine, okay, and now we take X and Z as proton Hc and Hd, but Y is being replaced by bromine, then you can see that free rotation doesn't actually give rise to this kind of geometries here. Okay, so that means these with respect to each of the substituents here, bromine and chlorine, these protons are not in same chemical environments in each of these configurations. Okay, so these protons, proton A will give peak in the NMR spectrum, whereas protons C and D will give two different peaks in the NMR spectrum, different ppm values. Okay, so again, once we replace one of the hydrogens on the oxide carbon with the chlorine, you can see that each of these rotation motion, carbon-carbon single bond rotation motion, actually gives rise to two different configurations, and from these configurations you can infer that the electronic environment that is being experienced in each of these configurations around proton A, proton B, and proton C are different. Okay, so essentially you will get a different peak for set of protons A and B, and then protons C in the NMR spectrum. So as we have seen, protons in a molecule in different chemical environments, okay, that means chemically non-equivalent protons can give different peaks in the NMR spectrum, which is evident in the NMR spectrum of benzyl acetate taken at 60 megahertz. So this one is a structure. So if you count the number of the types of protons here, you can see that there is CS3 proton, CS2 proton, and 5 phenyl protons here. So if you try to apply the principle of applying a symmetry operation, then you will be able to see that the CS3 proton is entirely in a entirely different electronic environment or chemical environment compared to CS2 protons and the phenyl protons, and so do the CS2 protons. CS2 proton is in an entirely different chemical environment with respect to CS3 protons and phenyl protons. Okay, so all the three sets of protons, CS3, CS2, and phenyl protons, are in entirely different electronic environments. So all these three sets of protons, CS3, CS2, and 5 phenyl protons, form three different sets of chemically non-equivalent nuclei. Okay, so all the three protons in methyl group are chemically equivalent with respect to each other. 2 protons in CS2 protons are chemically equivalent with respect to each other. 5 phenyl protons in benzene are chemically equivalent with respect to each other. So all these sets of protons on its own makes chemically equivalent sets of protons, but when you compare them, all the three sets together, you can see that three sets are chemically non-equivalent with respect to each other. Okay, so you can see that the CS3 protons, this methyl protons, gives an intense peak at around 2 delta value, because these are the most shielded protons. Then CS2 protons, which since they are being connected to the phenyl ring, gives a peak around 5 delta value. Okay, then the phenyl protons, due to magnetic anisotropy, they are highly deshielded and gives a peak around 7.2 delta right here. Okay, and you can see that the peak intensity of each of the protons are entirely different. Okay, so if you take the integrated area under this each peaks, okay, integrated area can be expressed in different units, and we have taken it as divisions under the peaks here. Okay, so you can see that the integrated area under this peak is around 32.5 divisions, and the integrated area under this peak is 22 divisions, and the integrated area under this peak is 55.5 divisions. Okay, so if you take the lowest integrated area, that is 22 divisions, and divide all the integrated area by this value, okay, you get these values here. So 55 divided by 55.5 divided by 22 is 2.52, then 22 divided by 22 is 1, then 32.5 divided by 22 given here is 1.48. okay, and right now if you write down the ratio, 2.5 is to 1 is to 1.48 here, and then if you multiply this one with a factor of 2 in order to make it a whole number, then 2.52 gives a value 5, 1 gives a value 2, then 1.48 gives a value of 3. So that's exactly the number of protons associated with each of these peaks. Okay, so this peak 2.52, which is associated with this peak, is actually due to 5 protons, which is a part of the phenyl ring here. Okay, then a division of 1 associated with this peak gives a value 2. So this peak is due to 2 protons, which is from the CH2 functional group here. Okay, then the division of 1.48, which is related to this peak, gives a value of 3, which are 3 protons, okay, due to the methyl group here. So you can find out which functional group gives which peak in the spectrum, or in a retrospect you can say by analyzing the integrated area you can find out the number of protons that gives rise to that typical peak in the NMR spectrum. So the integrated area or peak intensity in an NMR spectrophotometer is a measure of the number of protons that gives rise to that typical peak. Okay, so what happens is we talked about chemically equivalent nuclei, and what happens is when you have a proton in a molecule, proton nucleus, NMR active proton nucleus in the molecule, this proton can actually interact with the equivalent protons on the carbons next to it. Okay, so you have got a proton on a carbon in a molecule, and this proton can interact with the chemically equivalent protons on other carbons in the same molecule. Okay, and as a result of this interaction, the NMR spectrum, NMR peak of the proton we are talking about can be split into several peaks. Okay, say for example, if our proton spin interact with the n number of equivalent protons on carbons next to this proton, okay, then the resonance peak of our proton will be split into n+1 components. Okay, say for example, if we have a proton or a number of protons in chemically equivalent environments on the same carbon, okay, then if it interacts with the 3 protons on the adjacent carbon, chemically equivalent protons on adjacent carbon, then the peak of our proton will be split into 3+1. That is a quadruplet. Okay, or if our proton or protons, chemically equivalent protons, interact with the 2 chemically equivalent protons on other carbon, then the peak of our carbon of our proton will be split into 2+1, 3. That means a triplet. Okay, so this is called spin-spin coupling, where during this interaction the spin state of our nuclear spin state of our proton or set of chemically equivalent protons couples with the spin state, nuclear spin states of the chemically equivalent protons on adjacent carbons. Okay, so the extent of this interaction or coupling is normally measured by a parameter called chemical or spin-spin coupling parameter, which is represented as capital J. Okay, and we shall see how this spin-spin coupling happens in detail later. Okay, so here is an example of the NMR spectrum of 112 trichloroethane measured at 60 megahertz, which shows the spin-spin coupling mechanism. Okay, so if you can see the structure. So if you see the structure here, you can see that we have got a proton on this carbon and we have got 2 protons on this carbon. Okay, so as far as these 2 protons are concerned, they are bound to the same carbon, and these two protons are chemically equivalent with respect to each other. Okay, so these two protons should give an NMR spectrum at the same frequency in the NMR spectrum. Whereas compared to this one, this proton is in a different chemical environment where this, or electronic environment where this proton is bound to a carbon which is bound to two chlorines. Okay, so this proton is chemically or electronically non-equivalent compared to these two sets of protons. So it should give the peak in the NMR spectrum at a different frequency compared to, or different ppm value compared to these two sets of protons. Okay, so that's for example we see here. So we see that the CH2 proton, which is much shielded compared to the CH proton, because we have got only one chlorine atom bound to this carbon. It is the peak of this one is shown here. Okay, so we expect only a single peak for the CH2 protons. Okay, but rather we see a doublet, and the spectra of this proton, NMR peak of this proton, which is should be much more d-shielded compared to these two sets of protons, because we have two electronegative substituents on this carbon, appears at a higher delta value, and we should actually in principle should see only a single peak for this proton here, but actually we see something like a triplet pattern. Okay, so it is this coupling or this multiplet pattern for these two peaks are due to the coupling of the spin states of these two sets of protons. Okay, for example, this proton, the spin state or nuclear spin state of this proton can couple with the nuclear spin states of these two protons. Okay, and as a result, since we have to the number of protons here are 2, n is 2, then the peak of this proton will be split into 2 plus 1, 3. So the peak of this proton is split into 3, and we call this peak pattern as a triplet peak pattern. Okay, and the ratios are in ratio, the intensity of the peaks are in ratio 1:2:1. We'll see why this is, the ratio is like this. Okay, and as far as the peak of CH2 protons are concerned, the CH2 protons coupled with the one proton here, so the number of proton it can couple is n is equal to 1 here, so n plus 1 is 1 plus 1 2. So the peak of CH2 protons will be split into two peaks, and we call this peak pattern as a doublet pattern, and the intensity of these two peaks are almost 1:1 ratio, and we shall see why it is so. And you can see the peak of TMS here. So this spectrum manifests the peak splitting pattern due to the spin-spin coupling of the nuclear spin states of chemically equivalent protons in the same nuclear spin system. Okay, so in addition to chemical equivalence, we can define something else called a magnetic equivalence or magnetic non-equivalence. Okay, so this is called in other words as spin coupling equivalence. Okay, so magnetic equivalence is a factor which is defined as we have, say for example, if we have say if you take CH3 protons, methyl protons. Okay, so and if you label the CH3 protons are proton A, proton B, and proton C. Okay, then if you just consider proton A and B, all these three protons are in same electronic environments, so these three protons are chemically equivalent to each other. And if you just consider proton A and B, proton A will couple to proton C or interact with the spin state of proton C, and proton B can interact with the proton spin state of proton C. Okay, so both proton A and proton B can separately interact with the spin state of proton C or coupled with the spin state of proton C. Okay, so and you can now guess that the interaction, extent of interaction between or coupling between proton A and proton C will be exactly is equal to the extent of interaction between proton A and proton B and proton C. Okay, so in that case we call proton A and proton B as magnetically equivalent. Okay, so however, hypothetically, if the coupling strength between proton A and C is not equal to the coupling strength between proton B and C, then we say that proton A and B are magnetically non-equivalent. So that is the basic concept of magnetic equivalence or magnetic non-equivalence. So we say that two chemical shift equivalent protons, so you need to note this one, the protons should be chemically equivalent. So two chemical shift equivalent protons are magnetically equivalent if they are symmetrically disposed with respect to each proton in the spin system. So our proton A and B are symmetrically disposed with respect to proton C in the same methyl proton spin system. Therefore, proton A and B are magnetically non-equivalent. Okay. In other words, if two chemical shift equivalent protons A and B in the system, the same multiplet couple equally to every other proton in the spin system. So in our case, for methyl protons, every other proton is proton C. Okay. So proton A and B couple, if they couple equally to proton C, then the proton A and B can be called magnetically equivalent. Okay. Otherwise, they are magnetically non-equivalent. So we have got prerequisites here. Magnetically equivalent protons should be having the same chemical shift value, or magnetically equivalent protons should be chemical shift equivalent. Okay. So we say that the magnetically equivalent protons should be isochronous. Okay. So they should have the same chemical shift value, or means these magnetically equivalent protons should give NMR spectrum exactly at the same frequency or same ppm in the NMR spectrum. Okay. And again, magnetically equivalent protons, nuclei should couple equally to all other nuclei in the molecule. Okay. That means the extent of coupling between the magnetically equivalent protons with the other proton nuclei within the molecule should be the same. They should have the same J value of interaction. Okay. So both chemically and magnetically equivalent nuclei gives a single peak in the NMR spectrum. That is obvious. Okay. So there are some notations that represents whether a set of protons are magnetically equivalent or not. Okay. So those are called popular notations. And in popular notation, chemically equivalent nuclei are represented as nuclei A2. Okay. The A2 means two nuclei A and nuclei A. Okay. So they are chemically equivalent. So it's something like a in alphabetical order, both A and A are equivalent, right? So chemically equivalent nuclei are similarly considered as two A letters. Okay, A2, or they are labeled as 2A, proton A and proton A. Okay, or B2. Okay, we can call it as B2 or X2. Okay, and chemically non-equivalent nuclei are called A prime. Okay, the first proton, say for example HA, the second proton HA prime. That means both proton HA and HA prime are chemically non-equivalent. Or B prime, HB prime, or XX prime, HX prime. Okay, so this is the way popularly notated or denoted the chemically equivalent or chemically non-equivalent nuclei. Okay, so here we shall see some magnetically non-equivalent protons. Okay, so if we consider this para disubstituted benzene, you can see proton A prime, okay, B prime. Okay, so the interaction between proton A and proton B here happens usually the spin coupling, which we shall see later. The spin coupling usually happens through the intervening bonds, chemical bonds between the protons. Okay, so there are two bonds between these two protons. Okay, usually the bonds between the protons is counted. So 1, 2, 3. So 3 represents the number of bonds between the coupling nuclei. Okay, so since coupling happens through three bonds, we represent the coupling constant as 3J. Okay, whereas if you consider A prime nucleus and B nucleus, you can see that there are 1, 2, 3, 4, 5 bonds between these two nuclei. And so if any coupling happens between these two HA prime and HB nuclei, it should be a 5J coupling. Okay, the coupling constant should be represented by 5J. Okay, so obviously the extent of interaction between these two nuclei and these two sets of nuclei are different. Okay, so that means these nuclei and these nuclei couple to the same nuclei in the system to different extents. Okay, so therefore HA and HA prime are magnetically non-equivalent nuclei. Okay, so similarly you can see that we have HA is disposed with respect to A nucleus, Fn nucleus in a cis configuration, whereas HA is disposed with respect to B nucleus, Fb nucleus in a trans configuration. Okay, so the coupling between these two are a function of these two configurations. So we get a coupling between cis configured nuclei. So we call this one as J cis, and coupling between these two are trans coupling. Okay, J trans. So you normally the extent of coupling between trans configuration is a little bit stronger than the extent of coupling between cis configured nuclei. Okay, so J trans is slightly greater than J cis. Okay, so because of this reason, you can say that these nuclei or HA or say for example, if you take FA and FB, both can be considered as magnetically non-equivalent nuclei. Okay, and say for example, for this molecule, re-rotation should be possible about carbon-carbon single bond, but in a hypothetical situation, if re-rotation is locked for some reason, say for example, if you take the molecule in a rigid solid state condition at a very low temperature, then free rotation could be locked. In such case, you can, if you consider this molecule, these two nuclei here in the molecule HA prime and HB prime. Okay, so if you consider, say, the interaction between HA prime and HB here, okay, the extent of interaction between HA prime and HB would be entirely different from the extent of coupling between HB prime and HB here. Okay, so then you can say that HA prime and HB prime are magnetically non-equivalent. Okay, so and I leave the last example to you, 1-chloropropane, where you can identify magnetically non-equivalent protons. Okay, so this magnetic equivalence or non-equivalence can be due to specific stereochemistry of the molecule as well. Okay, so the first case here, case A, shows a homotopy molecular system where you have got two protons here, A proton and B proton. So if you replace any one of the proton with another atom, for example atom A, then you get another configuration. Okay, so for example, if you replace HA with A, you get this configuration, and if you replace proton B with A, then you get this configuration. But you can see that the stereochemistry suggests that these two protons are these two molecules are identical. Okay, so that's what this homotopic molecule means. Okay, so though these molecules, these two molecules are not chiral. Okay, they don't have a chiral carbon center. Okay, an example is this one. So in such a molecular system, if you replace either HA or HB, okay, with the CS3 or both with the CS3, then these are derived from a homotopy system, and in the absence of any coupling, these two methyl protons will be isochronous. So that means in the absence of coupling with any other protons in the molecular system, these two methyl protons will be isochronous, and they will have the same chemical shift value, and they give a single peak in the NMR spectrum. Okay, but if you consider an anisotropic molecular system, where if you replace either proton A or proton B with another atom or another functional group designated by A here, then you get two enantiomers. Okay, you get two enantiomers, and this one is an example of these two protons are anisotropic protons. Okay, so for two such protons, if these two protons doesn't couple with any other molecule in the same molecule, in any other proton in the same molecule, or if this if there is a lack of chiral environment in the molecule, then these two protons are isochronous. That means they are chemically equivalent, and they gives rise to a single peak in the NMR spectrum. Okay, and finally we consider two diastereotopic type molecular system. Okay, where we have XY, HA and HB, where Y is a functional group which contains a stereo center, a stereoscopic carbon, stereo center carbon or stereocarbon center, and if you replace HA or HB with the atom or functional group A, okay, then you can create a diastereomer, set of diastereomers. Okay, so here in this case, these two this molecule is an example. These two protons are diastereotopic protons, and these two methyl groups are diastereotopic methyls. Okay, so you can see that these two protons are no longer chemically equivalent. If you apply any kind of a symmetry operation on the molecule, then you can see that these two protons are not chemically equivalent. And again, neither do these methyl groups are chemically equivalent if you apply any symmetry operations or spontaneous rapid process on the molecule. Okay, so these are these molecules, these protons are not isochronous. They give different peaks in the NMR spectrum. Again, these three methyl groups are not isochronous. They give different peaks in the NMR spectrum. So these two sets of these protons or these methyl groups are not isochronous. They are not neither magnetically equivalent. Okay. Again, if you consider this type of molecular system here, and which could be a diastereotopic molecular system, and if you replace this proton A with an atom or function group A, then you could generate stereo centers on this carbon and this carbon. Okay. So these are basically diastereomers, and this one is an example. These two protons are diastereotopic protons, and by applying the same principle of the application of molecular symmetry operation or rapid process, you can see that none of these sets of protons or pairs of protons are neither isochronous or nor they are magnetically equivalent. So these two protons will give two different peaks in the NMR spectrum, and these two protons will give two different peaks in the NMR spectrum. So here is an example, typical example showing how the stereochemistry affects the peak positions of protons. Okay, so if you consider the case here, if you consider this here, this proton, C3 proton, the first methyl proton can be seen right here, and this methyl proton and this methyl protons can be seen as almost like a doublet type pattern here. Okay, so one of the peaks could be due to one of these methyl protons, and one of these peaks could be due to this one of these methyl protons. Okay, then OH is the OH proton peak is not so much remarkable. You can see this one right here at 1.5. Okay, and the proton of HD proton can be seen at as a multiplet pattern at around 1.7, and the proton HC, which is highly d-shielded, can be found just below 4 here. But what you need to look at is proton A and proton B. Okay, so this molecule is actually an example of an anisotropic or diastereotopic molecular system. So for this diastereotopic molecular system, proton A, if you apply the concept of a symmetry operation or rapid process on the molecule, you can see that proton A and proton B are not chemically equivalent. They are not isochronous, they are not magnetically equivalent as well. Okay, so these two protons will have two different frequencies in the NMR spectrum, and also they couple to other protons in the NMR in the molecule, other protons in the molecule to different extents. Okay, that means they are not magnetically equivalent as well. Okay, so here is a peak of proton B here. Okay, and you can see the proton A is seen at a different frequency, and both the peaks have got different multiplet patterns, indicating that they have different extents of coupling with the other protons in the same molecule.